Okay, we're going to do our very first conservation of energy question. What that means is we have to have a situation. So here's what I'm going to do. I'm going to take just a regular mass, 1 kilogram mass specifically. I'm going to have it traveling at 3 meters per second, and this thing is going to be frictionless, which means then that this will be a constant velocity of 3 meters per second. It's going to be traveling this way, and it's going to end up hitting a spring that's secured onto a wall or something like that. I'm going to tell you that the spring is going to have a K value of 50 Newton meters. That means it takes 50 newtons to stretch at 1 meter. And what I want to know, first of all, for A, I want to know the maximum compression. Okay, that means that I'd like to know that when this thing hits, how far is this going to squish? So I want to basically know my maximum X, and that occurs when your velocity is 0. Your final velocity, I guess, is 0 meters per second. So right here, it'll squish, stop, then it'll start shooting back eventually. So what I need to do is do my conservation of energy formula, which means I have kinetic initial, I have elastic initial, I have kinetic final, and I have elastic final. So that means that I'm going to go 1/2 mv squared plus, I know I have no spring compression in the beginning, so no energy stored there, so this is going to go to 0, plus 0. I also know that based on this maximum compression that I have no kinetic energy here, so that goes to 0, plus 1/2 kx squared. Plugging this in, 1/2, my mass was 1 kilogram, my velocity is 3 meters per second, my K value is 50, and I want to know the compression. So 3 squared is 9 times 1/2, that's 4.5 equals 25 x squared. So x squared is going to end up being 4.5 divided by 25, which means then that, I guess I'll come up here, that x is going to end up being equal to 0.42 meters. Which, as a decimal, 0.42 is not much, but if you think of it in terms of centimeters, 42 centimeters, that's a pretty good bit of compression for this spring. So now, that's my maximum compression. For part B, what we'll do is, let's say that, well, what's going to end up happening is this is going to squish in, it's going to stop, and then it's going to shoot this brick back out. We are going to find the velocity when the spring is still compressed. Velocity when spring is compressed. So still at x equals 20 centimeters. So there's two possible answers here, because you can be compressed 20 on the way in, and then you compress all the way to 42, and then you're going to be coming back out and you're going to pass that 20 again. So we're going to get a velocity that could be plus or minus. So probably would have been better to have just asked for speed. But we'll do velocity. So again, I have to make my conservation. EKI plus EEI, EKF plus EEF. My kinetic energy in the beginning is still 1/2. My mass is 1, 3 squared. There still is no energy being added by that spring, but now I want to know how much velocity my 1 kilogram has when I only have 20 in my energy. 0.2 squared. Okay, so that means that this energy plus this energy is going to end up equaling all of that energy, which is what we know. So this is 4.5 equals 0.5 v squared plus 25 times 0.04, which is 1. So 4.5 equals 0.5 v squared plus 1. So solving this all out, I end up getting a velocity of 2.64 meters per second. And that can be plus or minus. And that makes sense, because it's less than the 3 original that was coming in. So there you go. And I guess I'll just put left or right. Or else I could have put plus or minus here, or else I could have just asked for speed and then just put 2.64. There you go.